Good evening, everyone. I am Nishant Churiwal from Consulting and Analytics Club IIT Guwahati, and it is my pleasure to welcome you all to today's session on real-time data processing. We are thrilled to have with us Sergey, a distinguished expert in high-performance computing and scalable systems. He is currently an architect and lead software engineer at Pathway, where he builds real-time data pipelines for modern applications. Previously, he led the delivery platform at Yandex, Russia's Google, as head of service, overseeing everything from architecture to team leadership. Sergey is also a three-time IOI medalist, including a gold, and has contributed to top-performing contests like the Code Chef, Snackdown, World Finals as a problem setter. We are honored to have him with us today. Please join me in giving a warm welcome to Sergey. Sir, it's all yours.
Thank you, Nishant. I guess we can start. As introduced a few moments ago, currently I work at Pathway, where we create a framework which can be used for RAG and for ETL. And today we are going to focus more on the ETL side of things, which is ELT and ETL pipelines. Our plan for today is in general two parts. The first part is where we discuss what is ETL and ELT and why do we need them at all, why do we need those concepts and when they are applicable. And then we do a little case study where we take an industry project and we analyze how ETL and ELT can be applied there and what are the implications of those architectures. So let's start. And this slide, while we are on this slide, let's discuss one of the main implications for ETL and ELT. To do that, we can imagine an organization that does virtually any kind of business. For me, I worked more in B2C businesses, so I have a bit more experience on describing them. And every business that is large enough consists of several departments. And there are always separate developer department, those who write the backend, and the department that is in charge of analytics and machine learning. So there are two teams, two worlds, those who are focused on the backend and on things that on their tasks that make things work right now in the real time. And those who do analytics, who evaluate the business results, who do pricing, for example, and they have different sets of tasks. So question is, why cannot they work and operate over a single paradigm? Apparently they cannot, otherwise we wouldn't have had this talk. And they cannot because the developers for the backend and the analysts and the machine learning engineers have different tasks and different modes of operations. So if we take production database, we cannot just use the data from the production database to perform our analytical tasks. There are several evident reasons for that. One of those is that we often use the production database to store some metadata, for example, about the orders, about the users, and so on. And we need the OLTP databases just to ensure consistency for the current state of the world we are operating in. So it's often about the real-time data, and we need it for the capability of transactions that can be assured between different tables. But when it comes for the analytics, we don't do just simple selects, select for a single user, select for a single order, select for a single worker, and so on. We often cover the whole range of data in our queries when it comes to analytics, and it's not what we have in the backend. So it's two different purposes, and two different databases should be used for that. Then, if we say that, okay, let's analysts and backend engineers share the same data storage, the same database, often the task for the people who do analytics is more to perform the calculations for analytics, to train the models, and they wouldn't necessarily try to write the queries that would be optimal from the standpoint of the selected database. So it's always possible that you hire, for example, a junior engineer, they write a query, and this query kills a production database because it does select star and join, which is perfectly fine in terms of some Hadoop MapReduce work, but that just consumes enormous amount of resources in case of the backend. So in order to be on the safe side, we need to separate the production and the analytics backend. So the production systems can be locked, and wherever we block the production database and production system, the service is not working and the business is losing money. We need to be on the safe side. Also, the problem in the backend is that usually when you do backend, as a backend engineer, I can say that we don't always think about how the data needs to be shaped for the sake of analytics. So even if we don't have the problem with tables being locked and the resources are consumed, even if we consider that the resources are infinite, which is of course not the case, which is never the case, the data is not in the best shape for analytics. And the fifth reason is that often for the audit purposes, we need a clear transaction log that would reflect where the data came from and what was the change history. So at this point, I guess we all agreed that we need to separate the data into two kinds of systems, two different systems, each one shaped for its own purpose. And let's discuss what are the modern ways, the paradigms to do that. And in general, there are two. Two, as from the title, ETL, which stands for extract, transform, load, which means that we do some kind of a job that does three things. It first reads the data from, let's say, production database. For example, Postgres is often used in the backend, so it reads data from, let's say, Postgres. Then it does the transformation, so it shapes the data a little bit that it looks more suitable for analytics. And after this transformation, this data is loaded into another kind of database that supports more analytics-shaped queries, like, let's say, Hadoop. And it's all done within the same job. It's ETL. The second one is ELT. It's also a sort of new paradigm. And it's extract, load, transform, which is a little bit different. There are two main differences here. So when we are saying about ETL, we consider that all the job is done within one task, one job, one worker. When we say, well, there can be several workers, but it's like one entity that does all the work. Then in ELT, it's not like this, because in ELT, we can draw a line between EL and T. So we have two tasks. The first task is just to pick data as it is from the data storage and place it somewhere where we are going to do the analytics, HDFS, for example. We just take the data and we just place it as it is. No transformation, just extract and load, as simple as it is. And then, once we have the data already in our data storage, which is shaped for analytics, And we have them not in the good shape. We have them just as raw data, sometimes with errors, sometimes just most part of this data needs to be cleaned. We do the transformation. And the transformations are done within the storage. So we shift the computation, the task for computations, to the backend system that we used for storage. Usually it's some kind of MapReduce system. So it has upside that it's easy to do the extract load step. We don't create the job that does everything. It's always easier to separate. But the downside is that your compute needs to be more robust because all the further data transformation needs to be done within the compute. And there is no simple answer for when we should use what, because there are use cases for ETL and ELT. And for ETL, we can quickly walk through what it's good for. So first of all, when we think about ETL, what comes personally to my mind is the personal data handling, because all the laws for personal data protection, for GDPR and so on, are extremely strict. And if we have sensitive data somewhere, it's not even the passport number. If we have the email address, if we have the phone number, it's already sort of sensitive data. We need to prevent as much as possible for this data to get in from one place to another. And if we just do ELT in this case, then before the job, we had sensitive data in one source, in production database. And after we did our data export, we have it in the two data storages. We have it in both the production database and the cluster that we are going to use in analytics. And from the standpoint of personal data protection, it's a failure. And most likely you don't need this personal data at all to do your analytics, because I cannot imagine the type of analytics for which you might need, for example, the phone number. So most likely you will need to use ETL when it comes to personal data. Then you take the data from your production database. Then you apply some transformations that remove the personal identifiable information. And then you place the data in the analytics cluster, and it doesn't have the danger of data leaking away. Because also, if you spread the data from one system to another, there is gradually more people that have access to it, and you can never guarantee that everyone will be honest in terms of they wouldn't try to identify the user to find the rights of the user, for example, in a taxi service by the phone number. And so it's always better to anonymize. And sometimes there are needs for complex transformations in the ETL steps. So the downsides are connected with the upsides in a way. So if we do both extract and transformation, it requires more resources because we do more work. It can be harder to scale the compute because when we have the ELT, it's sort of easier because if we need more resources on transformation, we can only add them in the analytics cluster. It's often easier rather than adding them to some backend service that extracts data and places it somewhere. So it's also less flexibility because we need to do lots of things in one place. It always leads us to having less flexibility. Yeah, and it's often harder to reprocess the data. So when we switch to ELT, it has the upsides and downsides that were connected with what we have already discussed, because we do easier scaling If we need to have more robust transformations, we can just add the resources to analytics cluster, and that would be it. Because adding resources to an analytics cluster is always easier than scaling some backend task, which can probably be not so easily parallelizable. So when it comes to doing transformation with, let's say, MapReduce or any other analytics system, it always holds that you can add more resources and obtain horizontal scalability. When you extract the data, for example, by some timestamp field, so if you do some kind of ETL, it's much harder to parallelize it because it's the extraction step. It can be harder for you just to scale it. So it's a good idea to keep it as simple as it is. So because of that, ELT has easier scaling. Also, the good practice for ELT is to keep the raw data, because we read the data source. We place the data from the data source in our what is called bronze layer. We'll talk about it 2 slides later. But the fact is, when we do ELT, we always have the raw data in our analytics cluster, which allows us to implement more calculations later if we decide that we need more calculations, and it's easier to scale this pipeline in terms of adding more and more computations. And it helps us to iterate faster. Well, the downside is that, as we discussed with ETL, here we don't clean any personal information. So we need to have stronger data governance, because if we occasionally export the data and then we understood that it has some personally identifiable information, it can lead us to some troubles with audits department, which are really strict in big organizations. Also, as I have said, compute costs are shifted to the warehouse. Usually it's not a problem. Usually it's much easier to scale the warehouse rather than the job that just extracts the data. So it's better to decouple. But if it's a problem in your case, if, for example, you have much more resources on extraction pipeline than on the warehouse, then probably you can have a look at ETL. However, this case would be rather exotic. So at this point, we have discussed the concepts which we have, the ETL and the ELT, that we can use to move our data from production environment, which is not really suitable for doing analytics right in it, to some isolated environment, which we refer as analytics cluster. And at this point, we need to understand how we store this data in our analytics cluster, because there are 2 ways to store the data. The first one is traditional data warehouse, which is more like old school way. For the traditional data warehouse, I can give you, for example, like any modern or not so modern database that you take lies into this category. So if we take, for example, Cassandra or MongoDB or older iterations of Kafka, it's all traditional data warehouse in the sense that it's very coupled with the storage and the compute. So we place the data somewhere, and we cannot decide that we store data in one place and we use the compute from the other place by our choice. Our storage and our compute are tightly coupled. And recently, there were some ideas to decouple our object storage and our compute. And this architecture is well known as data warehouse. So in data warehouse, lakehouse, sorry. So in Data Lakehouse, you can select a backend for your data, and it's in practice any backend that supports key value storage operations, that is put some value by some key, and that supports listing objects under some prefix. It most likely will be enough for this type of storage. So you can pick whatever you want. You can pick S3 because it's infinite and not so expensive. You can pick Azure Blob Storage. You can hold it locally. For example, you can organize some RAID, for example, on your servers and place the data on your servers. And for compute, you can select whatever engine you want. So you can select Spark, you can select the various SQL engines, and you can use them. So it simplifies data migration. For example, you do a startup, and in the startup you have very small servers, and you and then you understand that's okay, let's buy more servers. We don't have enough disk space to store the analytics for 5 last years on our just local machine. And you can easily migrate this data for S3 or Azure Blob Storage, and you can easily scale the compute as well. And you don't have to scale two at once, as you would with traditional data storage engines. You are more flexible. At the same time, they support both structured and unstructured data and ACID transactions. So there is a thing which is called Delta Log in, for example, Delta Lake, which I would refer as an exemplary data lakehouse. There is also, for example, Apache Iceberg. So there are several solutions that have similar paradigm, but just to be more concrete, let's speak about Delta Lake. So there is transaction log, and there are transactions in this kind of engines. So you still have the guarantees on data integrity. And as we have discussed before, it's flexible and scalable. And if you want to use Spark, it works with it. So we have discussed a little bit about Data Lakehouse. Let's sum it up. So you decide where to store the data. You choose the compute, whatever you want. You scale them independently, and you save money on scaling only what you need and when you need. It supports ACID. Since we have already discussed the advantages and disadvantages of this way to store data, we can proceed to the next important concept, which is particularly important when we do the ELT kind of task that we extract, load, and then transform. But it's also useful in ETL as well. So this is called Medallion architecture, and it has several layers. Here on the image, there are 3 layers which are conveniently named bronze, silver, and gold. But of course, you can have more, and you can name them differently. It's just an example. The idea is when we do ELT, we extract data, and we place them in what we call the bronze layer. So our bronze layer is just the raw signals that we extract from everywhere, from the production database, from Kafka very often, and from other data sources as well. So bronze is raw data which is not suitable for processing, but we always have this data. And if we decide that we want to build a brand new pipeline, we don't need to ask our backend colleagues to export the data once again or to establish one more job, because we have all the data on the bronze layer. And this is the main purpose of the bronze layer. It doesn't have to be perfect in terms of data organization. It doesn't have to store the data conveniently for analytics, but it has all the data that we have exported it. And now we have it, and whatever pipeline we want to implement, we can implement it within our analytics team. We don't need to ask anyone else. So this is the bronze layer. And then we do gradual transformations to make this data of more and more quality, of better and better quality. So from the bronze layer, we implement transformation which cleans duplicates, for example, the data that removes the incorrect entries, the jobs that remove any trash from the data. And we have the silver layer, which is the optimized data, optimized for analytics. And then whenever we want to implement a new pipeline that produces something for the business-oriented user, for a person, for example, who makes a decision on anything, we do the data from silver layer, and we do the transformation and place the result in the gold layer. So gold is about having the data that can be directly used by some non-technical person. So you created a dashboard, and this is the data source for this dashboard. So it's the final result of our transformations. While silver is just the data from bronze, which have been cleaned and prepared a little bit. So this is just an example. The Medallion architecture is often referred as this. So if you Google for some articles or look elsewhere, you will find that Medallion architecture is several layers with, not even several, 3 with these names. But if your data pipeline is more complex, you can use more layers. So now we have discussed how we extract the data. We have decided how we store it. Based on your case, you can make this decision. And at this point, you can proceed to implementing your data pipeline. You will implement it, you will run it in production, and it will break. Let's discuss why and how. So the sources always have data quality issues. Even if we take the data from our production database, it doesn't guarantee everything, because we can have a hypothetical situation when there is a backend service and it breaks. The backend server has been broken. The business is not working. When user opens the app, they see nothing. They see that server is not available. And of course, in this situation, our colleagues from backend will be doing their utmost to make the service responsive again. And for example, to fix some invariant, they can delete some data from production database, or they can override some data in production database so that some invariant holds and the service starts to respond again, that it doesn't fail on the startup or so on. It's not a good practice, but it happens. And this is just an example when you can think that, well, it's our backend, we can trust this data, but in fact, no, we can never trust any external data, even if it's the data that is provided by the adjacent team that sits in the desk in 10 meters. Also, the problem can be that there can be a late data arrival, or even simpler, the external APIs that we pull can fail. For example, we decided to do the data export from a database, but the database is currently locked, or even the server for the service from which we want to extract the data is down. And we should handle it gracefully, because sometimes people are too strict on the conditions for the service, And if we don't process gracefully the situations when the API or even other service within organization is not available, then we are going to fail, while the better approach would be to do retries. It's a good practice to do retries with exponential back-off and random jitter that is added from one retry to another. But we need to take into consideration that any external service can be down. Then also a classic problem is that schema may change. Therefore, we need to be backward compatible in our schema, because often the data extraction jobs fail when we try to export the data for which someone has changed the format, and the insertion in whatever database or data lake or data storage we want to do doesn't work. Probably it's a good idea just to have as more generic schema as possible. If we can just store the data on the bronze layer as raw bytes, I would say it's not so bad to avoid this type of problem. And of course, there are pipeline failures. So it's not only external systems that may fail, it can also be us, because we can have bugs in code, we can have resource exhaustion, because our ETL or ELT job, it needs to run somewhere. It runs on the server, and the resources of the server can be exhausted, or some dependencies of our code dependency libraries, they may fail. And now we know all of that, and we need to do something to prevent it. So there are several patterns for how we need to act to have durable pipelines. One of the most important concepts is idempotent and incremental data processing, meaning that we don't need to reread data from scratch again and again. Because if we read the data from scratch again and again, it can work for now, but then a year passes and your data extraction job would take some ridiculous amount of time, and it would take some time for you to remember what is there and to fix it. So it's better to make all jobs incremental from the beginning, so that you memorize where you stepped last time, and then when you restart, you only read the chunk which has been added. And idempotent means that if you add some entry twice, it still reflects once in your data storage. The second thing is schema versioning, which would help us to prevent the problems when the schema has been changed. And of course, we need to make it backward compatible. In general, there is an advice to treat configuration as a code. That is to store all configuration that we have in some version control systems, because when something happens, we can easily see the history of changes and understand what was changed recently. So it also applies for the schema. We need retry mechanisms, because as we discussed, any external service may fail, but we should not. So we need to retry. We need to have monitorings and alertings. So if the resources on the server that does the data extraction work have been exhausted, it happens, but we need to know about it. So some alert system must be implemented. And of course, it's always good to have clear data documentation. So a little conclusion on the bottom of the slides is that it's impossible to avoid failures for any kind of service that we implement. For the backend, for the data analytics, for the extraction, failures will happen, but we need to build for failure. And when we do the data extraction job, we need to think how it will behave when some of the listed failures happen. If it can safely recover at any time, it means that we have built a good and durable data extraction job. Now, as promised, we know the main concepts of data extraction, and let's have a little example, partly hypothetical. However, I worked in right tech, so it's hypothetical but influenced by what I saw from the production use case. So suppose that you have a service like Uber for calling a taxi. So you select a point on the map, you press the button, the taxi arrives, you sit, you go somewhere, and that's it. We need to build the analytics backend for this service. We have two kinds of users in mind. The first kind of users are, let's say, investors and the persons who make business decisions, and they need to have clean and robust dashboards. And the second kind of users, which you will always have in this kind of B2C service, and in general, I think in any B2C service nowadays, are the ML engineers. And the ML engineers, they don't need the dashboards, but they need the features, and they need the features to be easily accessible. And so we need this. Of course, I need to make some disclaimer that in big companies, there are often some custom in-house solutions. Sometimes they make publications about their internal solutions. We will not discuss them because it's no use. I don't know the peculiarities of, for example, what Uber uses for analytics. So let's discuss about how we can use the well-known instruments to build our data pipelines. Here, we have started speaking about the features and the machine learning models. And we need also to understand that we will have a big variety of data sources. Because, of course, we will have some SQL data storage like Postgres or MySQL or whatever. We will most likely have the message queue for sending, for example, coordinates of the cars. But we need external context. We need the weather in a specific region. We need to know public holidays, for example. We need to know the information about road closures because it will cause surge in the pricing. And we need any other real-world signals. We can think of many. For example, they can be a concert, a very big concert planned somewhere, and it would also affect pricing in a certain time zone because we know that when the concert finishes, lots of people will leave the stadium and lots of them will call the car. And so there are lots of external sources that also need to be handled, and most likely it's the external APIs we have talked before. We will need to take the features from them as well, and we need to do it gracefully. Because it's not even our backend. It's something very external. We need to handle it gracefully. So here, the next thing we can discuss is what concept we need to use for building our data pipeline. We have ETL and we have ELT, as we discussed. And here I have several examples of the data sources. So since we are talking about the ride-sharing service, we will most likely have the coordinates of the cars, and it will be an important feature for the pricing because we will need to know the density of the cars within some polygon. And here we can safely use ELT because it's just raw coordinates from GPS. We can just take them and place somewhere in the Delta Lake, with which we have got acquainted several slides ago. And as we discussed, the bronze layer is very raw, unfiltered data. It can even consist, for example, coordinates like 0, 0. because when a car enters a tunnel, it stops producing any meaningful GPS signals and often sends just zeros. We have it, for example, in our LaPost pipeline. There is an article on Pathway website you can read. So the coordinates are never perfect, but we just take them and place at bronze layer. And then we have the silver and gold layers. And in case of coordinates, we often do the map matching. So let's say you have the stream of coordinates, but the cars can only move on roads in most cases. So what we do with, let's say, coordinates, we take these coordinates, we see to which road it corresponds, and then we change the coordinates in a way that a car was moving by a road. So we pick, for example, the nearest highway. There are many algorithms to connect raw coordinates with the road graph. After that, we have some meaningful information, for example, to build routers on top of this. Then, if we talk about Postgres or any other similar database, it will be used to store the information about users, orders, and so on, and to ensure consistency. So that if we have the information that user has a particular order or history of orders, it wouldn't contradict. So if we know that a user is going on some order on some particular car, that all will be connected in a relational database between themselves, and same for history. And here it's a little bit more questionable if we can use ELT, because anyway, it's easier to have personal information here. So what we can do thin ETL, where by thin, I mean that we take this data, we still try to place it on the bronze layer as it is, but we anonymize it. So we remove all user-related identifiers, and then we just place it on the bronze layer. Also, data extraction is not easy. And when I say it's not easy, I mean that even if we do simple queries that extract data from a database, it can still overload the database. So we should always think how we can reduce the load on the backend, on the data storage backend for our extraction. And for instance, with Postgres, the most installations have several replicas, where one replica is responsible for writes, and other replicas are responsible for reads. So if you do data extraction from this kind of system, you should definitely use the replica that is used for reads. And also, because if you use the replica that is used for writes, there is only one of them, and you sort of consuming resources of more precious replica. And also, if we look on replicas that are used for reads, there are sync and async replicas. It's a better idea to take the async replica because the data in the async replica can be late for several seconds. But if we are speaking about exporting all orders within the day or exporting features that we use in machine learning, then if this data arrives several seconds later, it's usually not a problem. Here also we develop this idea on extracting data. So if we extract data from Kafka, we can create a consumer group that just reads the data over this consumer group and writes it to our Delta Lake. When we have Postgres or any other system, it's much more difficult and it has caveats. There are two approaches to extract data from database. First is the Bayesian, and the Bayesian works as follows. So the database writes all changes that happen to the database in the write-ahead log. On the slide, it's WAL. And this data can be propagated to external reader if you create the replication slot. So we can do this, and the Bayesian listens to this replication slot and places the data in Kafka from which you can extract with a simple consumer group. But of course, if you ask a database to do more job, There are no miracles, and the database would work slower. So it's not the universal solution, and you cannot have it too much replication slots. So at some point, probably you would need to use something else. And the second option is to have the data organized in a way that there is a sequential ID, and when you do a write to a table that needs to be tracked, the new write creates the new sequential ID that is greater than the previous one. Then when we start again, we can see what was the last sequential ID and start reading incrementally. As we discussed, incrementally is always better. From the last read the sequential ID or timestamp. But it's also not perfect, and it also has problems, because if there are several parallel writers, they can write with different speeds. And one, suppose that we have the slower writer that writes the ID n, and the faster writer that writes ID n+1. So we have wrote the entry with ID n+1, but we still have the slower writer that has that's writing the entry with ID n, and we need not to lose this entry. So simply picking the maximum scene ID doesn't work here, and we need to have some backup mechanisms to detect those late entries and not to miss them. So it's also not a silver bullet. And the conclusion for those two slides is that data extraction is complex. There are many caveats, and there are many peculiarities that depend on particular data source from which you are doing the extraction. So this is one of the purposes of those tools, to simplify life for you and so provide you some solution which has been already verified by other engineers, that is stable, and that you don't have to reinvent from scratch. This is the point for ETL frameworks, at least one of the points. Here we also need to discuss how we ingest the data, and it's connected with what we discussed. From external features, the ingestion would be easier, because if we speak about weather, as we discussed, weather is a very good feature for pricing. Then we do many small polls to the external API. If those polls fail, we do retries. If retries don't help, we do alerting. And the engineer can check that the API has changed, for example, or the API key has expired. And if it fails, we can do something. But we can use ETL frameworks here as well, because when we use one framework to extract both internal and external features, they will be extracted in the same format. And then it would be easier for you to implement the jobs that would process the data from bronze layer and place it on the silver layer and further. And also another kind of disclaimer, we can store everything in Delta Lake or any other systems, but when it comes to production, bigger companies usually use the mechanism which is called feature store, which is the separate backend for features. So if you go to Uber, for example, or to Yango, which is also very popular as a ride-hailing service, then the features will most likely live separately. And we are approaching the end. And here, by this moment, we have already decided what will we extract, from which sources, what are the peculiarities, what we need to have in mind. So now we need to understand how we maintain our data storage, our analytical cluster. Because if we just blindly extract the data without caring for whatever system we have to store the data in the analytics cluster, it's going to break one day as well. So there are several patterns that are used, and one is partitioning. It's not the same partitioning as used in, for example, Kafka. It's partitioning by day and hour. So we select one column which has low granularity, for example, day, and we say that all the data is partitioned by this column, and it can be easily optimized. Let's say that we extract the data from the backend every 10 minutes. And then every 10 minutes, we write a chunk of data to Delta Lake, and we create a new entry in the transaction log. And this entry says, okay, we have taken this chunk of data and placed it here. Then the data is fragmented, and we have the problem that working with fragmented data is slow. And we need to reduce the fragmentation. And if we have the partitioning by day or by an hour, we can order the Delta Lake to compress all data that we have within a single partition, let's say within a single day, into one big chunk. And it's much more robust and efficient for you to then process this data with whatever compute you have, let's say, for example, Spark. It's done with optimize command. So let's say that you have partitioning by day, and you have the service that produces data every 10 minutes. It means that for 10 years, it will produce 144 10-minute intervals in the day, multiplied by 365 days in the year, and by 10 years. You will have several million chunks. It's impossible to produce gracefully and quickly. However, if you do the partitioning and the regular optimize, you will only have one chunk per day, meaning that you will have only 3,000 chunks, which is much more approachable for whatever compute you have to analyze quickly. So it's partitioning and optimization. Another thing which can be caveat is checkpoint management, because in many systems, when you write data, they create checkpoint for the current state of data from time to time, and those checkpoints accumulate, and it means that if you have checkpointing too frequent, the size of your analytics storage will grow quadratically. So you need to make sure that checkpointing does not create checkpoints too often. Or if it does, you probably need to remove the old checkpoints. Then there are good practices which are connected with data quality and reliability. So you need to reject broken data early. It's okay if the broken data is on the bronze layer, because this is one of the key ideas of ELT. You just take the data and export it as lightly as possible, but silver is a good place to reject the broken data. Don't assume that external data is clean, as an example with engineers who want to fix the backend database and change some data on it to ensure invariance. There are always some way to spoil your data, so never assume your data is clear, even if you take it from your other team within the organization. And handle the change of the schema gracefully. And in general, I would recommend to make schemas backwards compatible. If you make a new field, make it nullable always, and version the schemas. Finally, we have the fault tolerance, which needs to be enforced, because if you work in a big organization, the profits depend on the trustworthiness of your data and on the delivery of the data in a timely manner. So do it twice, do monitorings, and when doing monitorings, you will need to have several. there is a need to have a monitoring on the container health. So if there is a resource exhaustion, you would need to receive an SMS and do something with it, rather than leaving it broken without you knowing. There is a need for business sanity checks. For instance, if you use the ride-hailing service, there will be trips with the with price equal to 0, but there should not be too much of them. And the anomalies should be counted, and the number of anomalies should be lower than the specified threshold. And build for failure, be able to recover from whatever happens in the external world. So don't do full refresh. Full refresh, in practice, it works, but it works when the size of table is constant. For example, is the forecast schedule for the day, and you always have like 24 entries, which is the forecast for each hour, and designed for incremental tools with reliable IDs or timestamp or change tracking. Finally, keep your data available for the audit. If you use Delta Lake, it's convenient because you have the transaction log, and transaction log shows where the data comes from and when it comes into your pipeline. So you can use it. Probably if you use Delta Lake for a long period of time, you would be tempted to implement some kind of compression for the Delta log to remove the entries, for example, that point to the files that have been compressed into a single chunk. You can do this, but sometimes audit is strict, and you need to keep those old entries, even if they don't make sense for the analytics. They can probably make sense for the audit of the data. And that's it from me. Thank you very much for your attention and for coming at the talk. If you have any additional questions, you can reach me out, for example, by email, sergey@pathway.com, which you can see in the corner next to the number of the page. If there are any questions, I can answer them.
Yes, sir, I will dictate them to you. First question is from randomly boy. As students or early stage founder, where do we start around the problem statement in focus? What do you advise on this?
Could you repeat, please, the beginning of the question?
Yeah, sir. As students or early founders, where do we start around the problem statement in focus? What do you advise?
Maybe you can send, because I have some problem with headphones.
Okay, sir. I will say it again.
Okay, I'm sharing it. Just a second. I have sent the question on the chat.
Yeah. I read it. So if I understand the question correctly, is what is the advice for student or early stage founder? And it means like general advice for the approach. So if it comes to the things that are connected with the talk, the ETL. So if we talk about the ETL, then we need to understand, do we have private data or not? And if the data is not does not contain personal identifiable information, I would opt for ELT and then do the transformation within the transformation layer within, let's say, Delta Lake. So this is what I would recommend for understanding where to start for the data extraction jobs. And the good thing about ELT is that if you decide later that you want to build a different analytics pipeline, you still have everything on the bronze layer and you can start it again without redoing the extraction job. And it also scales very well because when your organization grows, you can just add more people to access the bronze layer and work with it. So I guess that would be my answer to this question. And I can proceed with other questions one by one, if that's okay with everyone.
That makes sense. You can.
Mm-hmm. Yeah. Then the question is, can the layer thing we talked about be extended to MCP architecture? So MCP is a very wide topic. I would say that we can extend it for MCP. For example, if we extract the data on the bronze layer, is definitely not applicable for MCP because it's raw. But then we do a silver layer that contains very high quality data, and the MCP can, if the MCP knows the schemas for whatever we have on the bronze layer, then it can use the data from the silver layer to produce the data to the gold layer. So in a way, yes. And in brief, it can be done in the following way. So you do ELT, you load the data into bronze layer. You don't do anything AI at this point. Then from the bronze layer to the silver layer, you implement the job that improves the quality of the data, removes duplicate, removes incorrect entries. And you have the good sources of data on the silver layer. Then you can bring the MCP in by defining the clear schemas for what you have on the silver layer. And then you can ask AI to implement, for example, the SQL queries and perform these SQL queries. So I would say that MCP can be used here by providing schemas and asking to provide the SQL query that needs to be executed to answer to some business request. This is one of the ways to implement it. Yeah. Let's produce to the next one. Can I use this approach to solve guardrails PII issues for my agentic application? Yes, of course. So similarly, as we discussed with the previous question, you can do ETL with the main goal of the ETL being to get rid of the sensitive information. Once you don't have the sensitive information and you have the clearly defined schema for whatever you have in your tables, you can further work with the agentic application, I suppose, agentic RAG, and use the clean and anonymized data for it. Next one. What is backward compatibility and how do you catch issues early, raise flags before it has occurred? So in general, the concept of backwards compatibility is that whatever change we do, it doesn't lead us to an error. So if we implement a job, it can work with any kind of the data that we had previously. This is the whole idea, so it's not so complicated. So if we change our data, if we extend it, we just need to make sure that our job still works well with both the old and the new data. And there are several rules of thumb for ensuring that. For instance, whenever you add a new column, obviously the old data wouldn't have this column. So it's a good idea to make it nullable, so that if this column doesn't contain some information for certain entries, for example, the old entries, your data processing job still works gracefully with it and doesn't fail. So that's the whole idea. And about raising flags before the problem has occurred, it's a little bit difficult. But what everyone does is that if your job fails, if it fails, for example, 3 times in a row, each time it fails, you send a signal, for example, in Grafana or any other monitoring and alerting systems. And those systems allow to configure the alerting rules, which are, for example, if we have 3 signals in the last 30 minutes, it means that we need to escalate. And escalate means to contact someone, to send an email, to send an SMS, to make a phone call. And that's basically it. It's hard to prevent it before the error has occurred. But what everyone does is we need to make sure that when the problem happens, we learn about it by the alert. So for the failures, we send the signals to, let's say, Grafana. We configure the rules for alerting, and we receive SMS or phone call whenever we have a problem. The next one is dynamic partitioning viable in a real-time delta ingestion. To my knowledge, no. We had a problem that we had a delta lake, and we wrote data to there, and we understood that we need to compress the data, but not all data, only the entries that are older than 2 weeks. And at this point, we realized that we need the partitioning by day, and it was impossible to add it just to Delta Lake manually. It is possible in some implementations like Databricks, but for us, what I did just a script that reads the data from one Delta Lake, the old one, and writes the data to another Delta Lake, the new one, the partitioned. If you use Pathway Framework, you can use it like in 3 or 4 lines of code, and that's how you can add a partition to a table in a way artificially, because you create the new lake that has the proper schema, but still there is a way to move from a non-partition table to a partition table by just rereading it and writing in the table that is properly configured. But overall, it's not so hard to foresee. You will definitely need the partitioning in Delta Lake, it's certain. So whenever you create a lake, I can say it's a good practice for you to understand how you will partition it and create the partitioning column. And it should not be anything complex. If you do partitioning by the day, it will most likely be enough, because the goal of the partitioning is for you to be able to compress the chunks, the many small chunks, so that your compute doesn't degrade within time. So the short answer is no, but there are several remarks. You can foresee it in advance, and even if you did not, you can still fix it by moving data from one table to another. Yeah, and the last one that I see, at least for now, is how does Pathway integrate with other data storage and data pipelines? So Pathway has the mechanism of connectors, and connector is basically a connector. You specify the parameters, the credentials for your data storage system, and Pathway handles it. There are documentation for different data sources, and it varies from data source to data source, because when we implement a connector, we first learn the peculiarities of data storage, and then we implement the connector with the usage of best practice that relate to this particular storage. And the best practices for Kafka, for example, are different from the best practices for Postgres, because they have different way to organize the data. They have different ways to store the data. Of course, there are some like common things like you need to implement retries and have them always everywhere. But when it comes to smaller implementation details, there is no like silver bullet. We learn the best practices to implement the connector to a certain data system, and then we implement it. And also we have enough users who report us if there is some bug. So of course we have different kinds of tests, like unit tests and integration tests, but we are also tested by our users and our clients who use the same set of connectors. So this is quite generic, but this is how we do with Pathway. Also, if we need lots of data sources, we are integrated with Airbyte, the library which is called Airbyte Serverless. So if you have your data pipeline done with Airbyte, it provides around 300 data sources. You can access the same 300 data sources with Pathway, because we allow using Airbyte data sources in our pipelines. And the recommended patterns for building end-to-end real-time data pipelines. Well, in general, we have discussed a few recommended patterns. So in general, this talk consists of the recommended patterns. Overall, if we give in the recommendations, I would recommend to stick to the ELT if it's possible, or to thin ETL if you need to remove the personally identifiable information. And then after you do that, I would recommend to do the Medallion architecture, which is very widespread nowadays, and just go with it. And don't forget about being fail-safe. And if something fails, just make sure you will learn about it in a short time frame, not after several days, because that happens sometime and consequences are never good. Yeah, I guess that was the last one. Are there any more questions?
No.
Huh?
No, thank you so much for an incredibly insightful session. On behalf of Consulting and Analytics Club, IIT Guwahati, I'd like to sincerely thank you for sharing your expertise on real-time data processing. Your talk offered a rare blend of technical depth and real-world perspective, and we truly learned a lot. Your journey from Yandex to Pathway and your contributions to the programming community is truly inspiring. We are grateful for your time and hope to host again in the future. Thank you once again.
Thank you. Thank you for being with me.